So, therefore, let us see what are the excess properties that we were dealing with, just as I have told you. So, therefore, if we go to the previous slide, it will be clear to you that what do we have then in this particular case? We have V excess. What is V excess? It is V actual minus V ideal. Actual, ideal, everything refers to solution. What is V actual then? It is sigma xi Vi bar. What is V ideal? You know, it is xi Vi. So, therefore, this should be xi Vi bar minus Vi. Had the solution been ideal, Vi bar would have been equal to Vi and Ve would have been equal to 0. In this case, this is not equal to 0. Therefore, what is this? It is actually the volume change on mixing of the solution. Same way we can write down He. Just the same way we can repeat it, H actual minus H ideal, right, which is nothing but equal to sigma xi Hi bar minus Hi, which is nothing but equal to delta H mixing for a real solution. Same thing, UE will be equal to U delta U mixing. Let us see what is GE equals to. For GE, what is this? Again, the same way it should be G actual minus G ideal. Okay. So, therefore, what is this? Remember one thing, this is the Gibbs free energy of the solution actual or the real solution. This is the Gibbs free energy of the ideal solution, both at same Tp composition. Now, remember one thing, as I had already mentioned, we cannot define absolute values of any properties. We always define the property changes, right. So, therefore, this actual Gibbs free energy of the solution is better expressed as the actual change in Gibbs free energy on forming the solution, isn't it? So, we had two components A, B, we mixed them. Due to this mixture, there was a change in Gibbs free energy. What is this Gibbs free energy change for a real solution? What is this Gibbs free energy change for an ideal solution? The difference between the two should be a better measure of the excess property as compared to the Gibbs free energy of actual solution minus the Gibbs free energy of the ideal solution. Why? Because we cannot define absolute value of Gibbs free energy for any particular substance in any particular state. We always need a datum, as you remember. So, therefore, this can be expressed as delta G m actual minus delta G m of mixing ideal, agreed, which can also be referred to as xi gi bar minus gi bar ideal. This is actual. Now, if you recollect what was delta Gm bar ideal, if you recollect, so therefore, Gi for an ideal solution, what was this? Your Gi bar ideal, or rather Gi ideal, let us take it. It was RT sigma xi ln xi, that we had already derived. So, therefore, what should this become? This should become xi gi bar actual minus sigma xi RT ln. So, we can take this out, or else we can define this as sigma xi gi bar minus gi minus RT sigma xi ln xi. I am sorry, this should have been gi bar actual minus gi. Agreed? Okay. So, therefore, what did I do? This delta Gm actual, that is actually the delta Gm change for the actual solution, which is given by this. The what happens during formation of the solution? The molar Gibbs free energy changes to the partial molar Gibbs free energy for each component I. So, this is for the actual solution and this is for the real solution, right. Now, tell me one thing, how is this Gi bar minus Gi related? This I will just repeat it once more so that it is easier for you to understand. G excess, this is equal to sigma xi Gi bar minus Gi minus RT sigma xi ln xi. Fine. What is this Gi bar minus Gi? This is phi because the pure component I was taken into a solution. That is why this particular change occurred. Can we not write it down as RT ln Fi bar by Fi? What does it show? The fugacity change of pure component I when it was taken into solution. So, what is my standard state in this particular case? Pure component I. So, from there, and the standard states are same for both the left hand side and right hand side of the equation. So, from the pure component I am taking it to the solution state, as a result of which its Gibbs free energy is changing to Gi bar and its fugacity is changing to Fi cap. Agreed? So, therefore, this particular equation, this particular exact equation can be written relating the molar Gibbs free energy or the partial molar Gibbs free energy with the fugacity and the partial molar fugacity. Agreed, I can do this. So, therefore, what is this Fi? Again, what is this Fi bar equals to? For a real solution, this is equals to gamma I xi Fi. So, therefore, can I not write this down as RT gamma I xi Fi by Fi? Both the cases, remember, the Fi are the same. It is the pure component fugacity at temperature pressure of the solution. This was the fugacity of the pure component and this is also the fugacity of the pure component. Can I not write it down in this particular way? So, therefore, what is my Gi bar minus Gi? Then in this case, this is RT ln, sorry, there was a sigma here which I forgot, sigma gamma I plus RT sigma ln xi. I can write it down in this particular way, fine. And so, therefore, if I substitute this in this particular equation, what do I get? X's Gibbs is nothing but sigma xi Gi bar minus Gi minus RT sigma xi ln xi. What is, I just substitute Gi bar minus Gi. So, what do I get? This is equal to sigma xi, RT can be taken outside, ln gamma I plus RT sigma xi ln xi minus RT sigma xi ln xi. And what do I get as a result of this? I find that the gamma I can be related in a very simple way with, this is the relationship of excess Gibbs free energy with gamma, right. And remember one thing, just because the solution is not ideal, so therefore, there will be some excess Gibbs free energy and that decides whether the solution forms spontaneously or not, and as a result of this non-ideality, gamma has come into picture. So, therefore, we find that the gamma of each and every component can be related to the molar Gibbs free energy change of the solution in this particular summation form. Now, what is this G, you tell me? G E is nothing but equals to your x into G I bar E, yes or no? Agreed. So, therefore, how can I get this G I bar E? This G I bar E, it is nothing but equal to del G E del x I at constant T P x j not equals to I. Agreed. Or in other words, can I not write it down in this particular way, del n I of, say suppose it is a you're a binary mixture. So, therefore, del this is G1 E is del N1 plus N2 into Ge at constant Tp N2. And what is this Ge equals to? This is nothing but equal to del N1 plus N2 x1 ln gamma 1 plus x2 ln gamma 2 constant Tp N2. Simply differentiate this and what do you get? You just differentiate it, you are going to get G by G I bar E, that is the excess, I will write it down, excess Gibbs free energy change, excess excess partial molar why the bar is there, excess partial molar Gibbs free energy change of component I in solution. What is this? This is GI bar E equals to RT ln gamma I. So, if you can calculate the excess Gibbs free energy, the partial molar excess Gibbs free energy of component I, then you should be in a position to calculate the activity coefficient of that particular component. Agreed? So, therefore, we find that we have come across these two equations which I have already written down here. If you observe, we find the the molar excess Gibbs free energy of the solution is given in terms of composition and activity coefficient by this equation, and the partial molar excess Gibbs free energy change of component I in solution is nothing but equal to ln of gamma I, right. So, therefore, this should be one particular way of finding out finding out gamma I, and it is important for you to recollect that just like we had done for ideal solutions, we can always write down, or rather we can always find out the excess entropy change of the solution. What it is going to be? This is nothing but equals to HE minus, if I write it down, for what is S equals to, recollect G equals to H minus Ts. So, therefore, S will be equal to G by T minus H by T, right. And therefore, once this equation was written for a molar quantity, we can always add a superscript S for the extensive properties, and this is the relationship between the excess properties. So, therefore, we can easily find out the Gibbs free energy, the excess entropy in terms of excess Gibbs free energy and the excess enthalpy, and once we do it, we find that the excess entropy is given by this particular equation, right. So, therefore, the interesting part which we found out was, the first thing which we found out, that definitely GI bar E by RT equals to ln gamma I. Gamma should also be related to other excess properties. How is it related? Let us see how gamma varies with temperature, pressure, composition, etc. Just try to do it yourself and then see what do you get. Suppose you try to find out del ln gamma I del T, right, at constant pressure and composition. What is this equals to? You already know what is ln gamma I. It is nothing but equals to GI bar E. Please do not forget, there are three things which have to be mentioned at constant P and X, right. And what is this GI bar E? This is nothing but equals to del T of mu I cap by RT at constant P and X, right. We can write it down in this particular way. So, therefore, from here what do we get then? From here we find out, or in other words, this can also be written down as, we can start it in a slightly different way and which will be easier for you to understand. Let us start from the basics, then it will be easier for you to understand. This we have already found out, right. So, therefore, what is ln FIL by FIL, pure component, nothing but equal to ln gamma I xi, or this is equals to R. So, if you have a RT here, you have a RT here, you have ln gamma I plus RT ln xi, agreed. So, what is del ln FIL by FIL, say del P if we take at constant temperature. Recollect what is this equal to? This will be equal to VI bar L minus VIL by RT. If you remember, dg equals to minus S dt plus V dp. So, therefore, this is what precisely we have done. So, in the same way, can we not write it down as del ln gamma I xi del P? This should be equal to VI bar L minus VIL by RT. What is VI bar L? It is the partial molar excess volume of component I in the liquid solution. What is this? It is the molar volume of component I in the liquid state. For an ideal solution, we know that if the for an ideal solution, what do we know? For an ideal solution, VI bar L ideal is nothing but equal to VIL. So, therefore, what is this then in that case? It is the partial molar volume change for the case of a real solution minus the partial molar volume change for an ideal solution. So, therefore, what is it then? This is nothing but VI excess by RT, VI bar excess by RT, agreed, which is what? This VI bar E excess. What is this? Excess partial excess E, bar means partial molar volume, agreed, for component I, which is nothing but actual molar volume of component I in solution minus the in real solution, real is within bracket, minus molar volume of component I in ideal solution, very important, at same Tpx. This you have to keep on adding because the standard states have to be the same, right? And therefore, and what is this del ln gamma I by del p? So, can we not write it down as del ln gamma I del p at constant t plus del ln xi del p at constant t? We know that xi, the mole fraction, does not change with pressure. So, therefore, del ln gamma I del p is nothing but it can be related to the excess partial molar volume for component I, which I have also written down in this particular equation. Same way, suppose we would like to find out the temperature, the dependence of gamma I on temperature. It should again go on in the same way. It should be del ln Fi del t at constant p. This is nothing, if you recollect, Hi0 minus Hi by RT square. Same way, can we not write down for the partial molar fugacity Hi0 minus Hi bar by RT square. So, therefore, can I not, and what do I know? I know Fi bar by Fi equals to gamma I xi, right. So, therefore, ln Fi bar by Fi, it is nothing but equal to ln gamma I plus ln xi, agreed. So, therefore, can I not write this down as del ln gamma? Again, I know that xi is not a function of temperature, the composition does not depend on temperature. So, can I not write this down as del ln Fi bar by Fi del t at constant p? Is this not equal to minus of Hi bar plus Hi by RT square? Hi0 is the same for both the equations. What is this equal to? Isn't it equal to minus Hi bar excess by RT square? What is this? This is nothing but the partial, I will write it down, Hi bar E. It is the partial molar enthalpy of component I. For partial, there is a bar, partial molar excess. See, I am also missing a lot of things. Partial molar excess enthalpy of component I, which is nothing but the partial molar enthalpy of I minus the molar enthalpy of component I at the same conditions of temperature and pressure, right. So, the variation with temperature can be related with the partial molar excess enthalpy of the solution, and the gamma I variation with pressure can be related with the partial molar excess volume of component I in the solution. And we know that the the gamma I, it is related with the excess Gibbs free energy of each and every partial molar Gibbs free energy of each and every component in the mixture by this equals to ln gamma I, and the excess molar Gibbs free energy of the mixture by this particular equation. So, therefore, we find, as we had anticipated, that excess properties arise due to the the deviation of the solution from the ideal behavior, and we have used gamma to account for this particular deviation. So, therefore, gamma can be related with the excess properties, and we have shown how it is related to excess molar Gibbs free energy of the solution, excess molar, the partial molar enthalpy of each component, excess partial molar volume of each particular component. Now, since we have defined another set of excess properties, it is very interesting to find out that these particular excess properties, they also obey the same equations as that of the molar properties as that of the total properties. Whatever equations we had defined in terms of total properties, in terms of molar properties, you just add a superscript E and you find that each and every particular relationship is applicable, and all these equations you can actually derive, and you can find it out that all these equations which are derived for your molar and total properties are applicable for total excess properties, for partial molar excess properties, for molar excess properties, right. Total excess properties given by this, your molar excess property is given by this, partial molar excess property for each component is given by this. So, these are the three symbols that we will be using. We should be little careful about the symbols, since we are dealing with a large number of properties, right. And there is one more thing which is very interesting. We have defined, rather we have tried to incorporate the non-ideal behavior by incorporating gamma. We have related gamma to the excess properties of the solution. Now, whenever we have been dealing with solutions, we found out that for mixtures there is a very important relation which tells us that all properties of the mixtures are not ideal. What was that particular equation? It was the Gibbs-Duhem equation. We had derived the Gibbs-Duhem equation in terms of chemical potential, right. The same can be derived for in terms of fugacity, and we should also be in a position to derive Gibbs-Duhem equation for activity coefficient. Why do we need to do it? We need to do it because we have seen that Gibbs-Duhem equation gives us one particular clue by which we can find out any property of component A if the same property for component B is known, provided it is a binary mixture. If it is a n component mixture, if we know the property for n minus 1 components, we will be in a position to find the same property for the nth component, provided the entire thing is being performed under the conditions of same temperature, pressure and composition. So, therefore, since finding out gamma is so very important, as far as vapor liquid equilibrium for non-ideal solutions are concerned, and we come across non-ideal solutions very frequently. So, therefore, it is important to find out gamma, or rather to express Gibbs-Duhem equation in terms of gamma, so that for a binary solution which we usually come across, if we know gamma 1, we will be in a position to find out gamma 2. Let us start from the beginning and see how we can derive the Gibbs-Duhem equation in terms of gamma. Remember the basic equation, it was S dt, minus V dp plus n d mu equals to 0. This we had found out for single component. Agreed? For multi-component, what should happen? The same equation, but this should be sigma should come up, n I d mu I equals to 0. This is for multi-component case. In terms of molar property, everything becomes small, plus sigma xi d mu I equals to 0 in terms of molar properties. Agreed? So, therefore, in terms of excess molar properties, again let us write down can I not write it down as mu I is nothing but g I bar E equals to 0, right? And again I know what is this g I bar E? we have derived it, it is nothing but RT ln gamma I. Agreed. So, therefore, instead of this di bar g, I can just write down RT ln gamma I. Then what happens to the Gibbs-Duhem equation? The Gibbs-Duhem equation then becomes SE dt minus VE dP plus sigma I equals to 1 to n or whatever xi d RT ln gamma I equals to 0. Agreed. We can write it down in this particular way. So, therefore, and now if we expand this part, what do we get? We get SE dt minus VE dP. I am just deriving it so that it will be easier for you. Xi r ln gamma I dt plus sigma xi RT d ln gamma I equals to 0. Agreed. So, therefore, what do I get? Finally, SE dt minus VE dP plus R written in a proper shape xi ln gamma I dt plus RT sigma xi d ln gamma I, this is equal to 0. Fine. What is SE equals to? It is nothing but equals to HE minus GE by T. We have already done it. What is this GE? Again, I would like to recollect GE by RT, it is equal to sigma xi ln gamma I, right. So, therefore, this particular term GE by T, can this not be written down as R sigma xi ln gamma I? Let us substitute it here. What do we get? Do we not get SE dt minus HE by T dt minus R, then this term and this term they cancel, these two terms, this and this they cancel out, and we get minus R sigma I equals to 1 to n xi ln gamma I dt. Fine. This particular term, this term then can be written down, this term can be written in this particular form. Okay. And so, therefore, on substituting this particular this and this in this equation, what do we get? We get equation like this, HE by T dt minus R, I have just substituted xi ln gamma I dt minus VE dP plus R sigma xi ln gamma I dt plus RT sigma xi d ln gamma I equals to 0. We immediately find that this and this they cancels out, and when all these cancels out, what is the final equation that we get? Final equation, it becomes HE by T dt minus VE dP plus RT sigma xi d ln gamma I equals to 0. This is the final equation, this is the Gibbs-Duhem equation in terms of activity coefficient gamma, right. So, therefore, this is the equation that we get under this particular condition. And then remember one thing, that when we are dealing with properties, this is what I have written down, this is the final equation that I have written down. So, this is the equation that we have obtained, right. Now, here I would like to mention one more thing before I go further. Since this is a property, therefore, we can have this particular derivation in an alternative form as well. Instead of starting from this particular way, we could have also started the Gibbs-Duhem equation in terms of mu, and we could have proceeded. At constant temperature and pressure, Gibbs-Duhem equation in terms of mu. In this particular case, we had started with gi bar in terms of fugacity or in terms of mu, suppose we write. We can also start with this particular equation. Okay. In terms of fugacity, this becomes xi d ln fi bar equals to 0, right. We know fi bar is nothing but equal to gamma I xi fi. Everything is for the liquid phase if you take. So, therefore, can I not write it down in this particular way, gamma I d, sorry, very sorry, xi d ln gamma I xi fi sigma, this is equals to 0, right. So, therefore, if we break it down, what happens? This is xi d ln gamma I plus sigma xi d ln xi plus sigma xi d ln fi equals to 0. This is a easier derivation, so that is why I am just doing it for you. Now, try to understand. We have started with constant temperature and pressure. At constant temperature and pressure, what is Fi equals to? It is the fugacity of the pure component liquid at the same conditions of temperature and pressure, and we know that for low to moderate pressure, it is the saturated vapor pressure. So, when T and P are constant, Fi automatically becomes constant. So, therefore, even if it is at low to moderate pressure or at any pressure, we know that this component becomes equal to 0. What about this part? This is nothing but equal to sigma xi dxi by xi, isn't it? Or in other words, this is sigma dxi. What is this? This sigma of dxi means the variation of the total number of moles. We know the total number of moles of the component is constant. So, therefore, automatically this becomes equal to 0. So, therefore, what does it imply? It implies that at constant T and P, automatically xi d ln gamma I equals to 0. Just the same equation which I had derived here, but this was the generalized expression. At constant T and P, this goes off. So, therefore, this is the equation which I have derived in this particular case as well, right. So, therefore, this is the generalized equation which we have. We find that at constant temperature, naturally this term goes off, and this is the equation. At constant pressure, this term goes off, and therefore, this is the equation. At constant temperature and pressure, I have derived this equation in two particular ways, and we find that this is the equation. Now, this equation, just like I told you previously, this equation is very, very important. Particularly, the importance or can be better appreciated if we can write it down in terms of a binary mixture. In terms of a binary mixture, how can we write down the equation? It is x1 d ln gamma 1 plus x2 d ln gamma 2 equals to 0. Agreed? So, therefore, from this particular equation, there are a number of important information that we can get, which we are going to discuss in the next class.